Welcome to another episode of X-Ray University. Today, we're going to be talking about the resolution of X-ray images. Now, our producer, Tony, he told me that you guys get bored with me talking for over half an hour. So this time, what we're going to do is we're going to split this video in three different parts. Part 1, 2, and 3. Part 1, we're going to be talking about what is the resolution of an X-ray image when you have a real X-ray source and an ideal detector. Then we're going to go and talk about, in the next video, how X-ray resolution works out when you have an ideal X-ray source and a real detector. And then lastly, on the third video, we're going to talk about a real X-ray source and a real detector. Now, if you don't want to go through all the details, just skip part 1 and 2, go directly to part 3 and get the answer. If you want a little more detail and work the math, then watch parts 1, 2, and then see what the final result is in part 3. All right, so let's get started with how an X-ray tube works. So we've covered this in previous videos, but I'm just going to give a quick refresh so we're all on the same page. So you have a filament that warms up, and as you warm up a filament, it creates free electrons that accelerate towards a target when we apply a voltage differential between the cathode and the anode. Upon hitting the target, these free electrons create X-ray photons using this brainstorm radiation process, and those X-ray photons exit the tube through a window. They can be made of aluminum or beryllium, or glass, depending on the energy levels you're interested in getting out of the tube. Now, depending on the spot size, right, depending on how small the target is, you end up with images like the one on the left, where you have a blurred image caused by the large spot size on the tube, or you can have a really nice image like you see here. I'm just focusing on the edges. You can perfectly see the edge of the bare die, the fillet, and the die attach. Even with the micro voids there, you can see everything. And when you use a micro focus, means the focus spot is micro, a few microns. With the mini focus, usually refer to spot sizes 30 microns and up. So even if it's 35 microns spot size, we call this mini focus. And then we also have sources in the nano focus level, where you have spot size in the nanometer level, which is even finer. Now, how does an ideal X-ray tube work? We have this really fancy animation here to show you. This round gray things are the X-ray photons. So they are generated by free electrons in the target, and they exit the tube in this location we're calling the focal spot. And then the idea of this animation to show you that every single X-ray photon on an ideal X-ray tube does not intersect the track of another X-ray photon, right? So as you can see in this slide here, all the tracks from the spot size to the detector is the gray object here on the bottom. All these tracks, they're not parallel to each other. Ideally, they would be parallel, but we have a cone beam. The important thing on an ideal X-ray tube is that those tracks do not intersect. So what does that mean? When you have a sample, it means that each of these tracks will cast a shadow that has a unique location on the detector, right? As you can see there. So it's a really nice, simple, straightforward connection between the track coming out of the focal spot on the X-ray source all the way there to the detector. Pretty straightforward. Unfortunately, that's not what happens in reality. In reality, we have a spot size that's larger than 0, which means that the tracks out of the X-rays, photons out of the X-ray tube, they do interact, right? And like you can see in this animation, and I drew the tracks here so you can see it better. And unfortunately, what happens is that as we cross those tracks, see what happens with the sample. that same spot on the sample is projected in two different locations on the detector. Let's look at the tracks here so you can get a better view. You see that what happens? So as you can see here, that edge of the sample, by the way, this is our sample, right? That edge on the sample shows up in this location of the detector and at the same location of the detector. And that's what causes that blurry lines at the edge of the sample. And that's exactly why the resolution of the image suffers. The larger this focal spot size, the worse your image quality is going to be. I hope that makes sense. And we call resolution that distance that's projected on the detector, right? So you want to have a resolution number that is as low as possible. What is the resolution for the ideal X-ray tube? 0, right? 0 microns, because there's no gap, there's no distance between the edge of the track and the next that projects on the other side, right? So let's look now side by side. On the left, you have a real X-ray tube where the spot size has a physical side. On the right, we have an ideal tube where that focal spot size is 0 microns, which means that every single X-ray photon does not interact with a neighbor, and as a result, you have a beautiful resolution of 0 on your detector. When you have a real X-ray tube, this focal spot has a dimension, and as a result, you end up with a resolution that is a number. But what is that number, right? You want to be able to calculate what is that number. So if you have a large spot size, as you can probably tell by now, that number is going to be larger, right? Because that penumbra that's going to be cast onto the detector is going to be larger. If you have the magnification change, as you can see here, you see the mag, I'm just lowering the magnification, moving the sample closer to the detector, right? So I'm lowering my magnification. By lowering my magnification, as you can see, that resolution number gets smaller, 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 right? So as you bring the sample closer to the detector, that resolution number is going to get smaller. Pretty cool. Now, what happens if you have a small spot size? When you have a small spot size, and again, going towards that ideal scenario, as you can see, that projection is already smaller, and as we remove or reduce the magnification, it gets smaller and smaller and smaller. So how do you calculate? Let's put some numbers behind it, right? I mean, theoretically, I think we all understand, we have an appreciation of the physical concepts that we're dealing with here, but how do you actually put numbers to it? So let's start with a sample that's really small, right? So small that we are able to capture the edges of the sample being projected here and here onto the detector. Now remember, part one of this trilogy, if you will, assumes that we have an ideal detector. What's an ideal detector? Pixel size is 0. So we have an infinite number of pixels on our detector, right? So as we look into putting numbers, the first thing we're going to quantify is the size of the spot size. So the focal spot size is area, right, or the dimension that we're going to generate the X-ray photons from. We're going to call that F. And the resolution of the source we call RS, which is this distance here. We're going to call this, which is the overall penumbra onto the detector, we call RS. Now, it's not going to be exact. There are some other factors that have to be taken into consideration. For example, the flux out of the X-ray source is not constant. We're assuming that's constant here. So it's not constant, so there are fewer photons on the edges of the beam than in the center of the beams, because it's a cone beam shaped flux coming out from the X-ray source. But for now, let's consider it a constant so that we can go through this calculation. As we saw before, the resolution, or RS, which is this number here, is a function of magnification. The lower the magnification, the smaller the resolution. So magnification will have to do with that, with this distance here. We know magnification is a function of 1 plus d2 over d1, and d2, or distance 2, is the distance between the sample and the detector. D1 is the distance between the sample and the source. All right, so here we have it all put together. We have the spot size here on the top, the resolution on the detector or the source here on the bottom. And how do we calculate this number as a function of the focal spot and the magnification? So I invite you to go back to your high school years, right, where you're dealing with pretty basic geometry. And these are what, if you remember, similar triangles, right? Similar triangles mean that, and here I cut them in half just to simplify, that angle alpha is equal on the top triangle to as it is on the bottom triangle, right? Because those photons are intersecting. And a very simple calculation here now tells you that the tangent of alpha is equal to f divided by 2 divided by d1. Similarly, tangent of alpha is also rs divided by 2 divided by d2. And then if I equal those two guys, tangent of alpha and tangent of alpha, what we get is that r divided by 2 d2 is equal to f divided by 2 d1, right? So what does it mean? It means that our rs, our resolution on the source, is equal to f d1 f times d2 divided by d1. Now we also know that magnification is 1 plus d2 over d1. Look at the factor showing up there again. And if we isolate that factor, we know that d2 divided by d1 is equal to magnification minus 1. Pretty straightforward. And we got a result that the resolution of the source is equal to f, which is the focal spot size, multiplied by magnification minus 1. So what does it mean, right? It means that if you have a system with a low mag and a large spot size, you're going to end up, so low mag, the sample is close to the detector, you get up with a tiny number here in your magnification, on your resolution. Similarly, if you have a low mag and a small spot size, right? It's also a very small numeric resolution. A high mag and a large spot size, big resolution number. High mag and small spot size, a smaller one. So here's to say that magnification plays a huge role in image resolution, meaning that if you lower the mag, you're going to improve resolution by quite a bit. And to a point where it doesn't really matter what X-ray source you have, within limits, of course. But as you increase magnification, as you go high mag, the dominant impact on the resolution becomes the spot size. So here we have 3 different sources, each with a specific focal spot, 15, 5, and 2 micrometers. And in the horizontal axis, we have magnification. Vertical axis, we have the resolution of the source on the image, right? The image resolution driven by the source. And very simple line, right? So as magnification goes up, as this number gets bigger, the resolution suffers, right? Linearly. And as you can see, when magnification is 1, meaning that the sample is right on top of the detector, the resolution is 0. It's perfect. Why? Because right now we're assuming that we have an ideal detector, right? And that's why all these lines start at 0. I hope that makes sense. So here's a couple of basically the matrix showing low mag with a large spot size here, low mag with a small spot size. We can actually see wire bones, fillet, and everything else. Higher mag with a large spot size where things get even worse. And then a high mag with a small spot size with the resolution drops, but we still get a pretty good image because we have a small spot size, small focus spot size. So what happens, what is the impact of the pixel size on the resolution? And that's going to be the topic for our next video. So if you want to learn what happens, what is the impact of a real detector on the image resolution, watch part 2. If you're bored and just want to figure out the final result, jump to part 3. See you next time. Thank you.